Hi, I'm Kaiyuan, a student at Northwestern University. This presentation is about our work on improving HDF5 write performance with log-based storage layout. It's a collaboration between Northwestern and the Argonne National Laboratory, supported by the DOE CP project. Before I start, I would like to thank the HDF5 user group for giving us this opportunity. So by default, HDF5 stores data sets in a contiguous storage layout that requires reorganizing data into canonical order. On I/O patterns with a large number of non-contiguous requests, the canonical storage layout often performs poorly due to high communication overhead in MPI collective I/O for reorganizing the data. The chunk storage layout supported by HDF5 alleviates this issue by limiting reordering within chunks, but does not eliminate it. The log-based storage layout always append the data in the file based on the order they are received. The resulting I/O pattern to the file system is always contiguous, regardless of the I/O pattern of the application. The expensive data reordering is delayed to when the data is read. However, it requires additional metadata to describe the location of the data, so a canonical view can be reconstructed later on. Here's an example of three H5 write operations. The I/O pattern in the contiguous layout is non-contiguous and interleaving, while the I/O pattern in the log-based storage layout is always contiguous. So this figure shows the relation of log-based VOL with other HDF5 components, interacts with both the native VOL and the file system. The log-based VOL stores its log data structure in an HDF5 file. The output file of the log-based VOL remains a valid HDF5 file, except that only log-based VOL can decode the content of datasets. Metadata operations such as group and attributes are handled through the native VOL to ensure compliance to HDF5 format. For better performance, the log VOL performs data I/O through MPI I/O directly that bypasses overhead in HDF5 dataset APIs. The log VOL creates a group to store the log data structure. Inside the group are several byte-typed datasets, some for log data and some for log metadata. Additional metadata are also stored as file attributes. For all user datasets, the log VOL creates it as a scalar dataset, with the original shape stored as a dataset attribute. It prevents the native VOL from allocating space for the dataset. Datasets are also assigned a unique ID within the file, so it can be referred to in the log metadata. I/O in log-based VOL is always aggregated. An H5 write call only posts the I/O request without writing any data to the file. The log VOL automatically aggregates the data and metadata into an internal buffer, so application can proceed as if it is a blocking I/O operation. The data is flushed to the log when the file is closing, or when the application calls H5F flush. The metadata is only flushed when the file is closing. We also introduced a new API that allows accessing multiple blocks within a dataset in a single call without additional overhead on data spaces. The Above is an example output file by a program that writes to a dataset twice with a call to file flush in between. So notice there are two datasets for data and the log structure, one for each flush. There's only one dataset for metadata since the metadata is only flushed once. We evaluate the log VLL with a benchmark that mimics the I/O kernel of the E3SM simulation framework. E3SM writes to hundreds of HDF5 datasets with a large number of fragments and non-contiguous requests distributed unevenly across the processes. The I/O pattern is actually inefficient for canonical storage layout to a degree that the native VLL cannot finish in a reasonable time. We ran the experiment on Corey's KNL node with 64 processes per node. We set the raster file system to use 16 megabytes stripe size and 128 stripes. We use HDF5's developer branch, but we also use the TAM and PIO developed by our group that optimize collective I/O performance with node local request aggregation. The E3SM benchmark output 5 files. The atmospheric component, referred to as the F case, writes 2 files using 21,600 processes. The first file contains 15 fixed-sized variables and 399 record variables with 1 record, totaling about 14 gigabytes. The second file contains 15 fixed-sized variables and 36 record variables with 25 records, totaling about 7 gigabytes. The oceanic component, referred to as the G case, runs on 9,600 processes. It writes 1 file containing 11 fixed-sized variables and 41 recorded variables with only 1 record, totaling about 80 gigabytes. The land component, referred to as I case, writes 2 files using 1,344 processes. The first file contains 18 fixed-size variables and 542 recorded variables with 240 records, with a total size of 86 gigabytes. The second file contains 10 fixed-sized variables and the same amount of recorded variables, but with only 1 record and a total size of only 370 megabytes. The results are shown above. The file opening time includes the time to create the HDF5 file and the group containing the log data structure. The time creating datasets and attributes include a time spent to define all E3SM datasets and to write all E3SM attributes. The I/O posting time is the time calling H5D write. The posting time for the first I case file, which is H0, is very high considering that no actual I/O is performed in the H5D write. The reason is a large number of data sets and the records that translates to more than 130,000 H5D write codes. The flush time is the time the log VLL writes the data to the log, including the creation of the data set for the data and other synchronizations. The difference across the files is due to different write amounts and a different number of processes used. The closing time includes the time flushing all log metadata and the time closing the HDF5 file. End-to-end time is the elapsed time between file open and the file close. The size of additional metadata generated by the log VLL is shown in the last row. Overall, the log VOL achieves a decent performance on an extremely complex E3SM I/O pattern. In this work, we presented a log-based storage layout for HDF5 datasets. We achieved a significant performance improvement over the native layout of HDF5. We are working on improving H5 DRAM performance, reducing metadata overhead, and improving scalability on GPFAs. Finally, we acknowledge the DOE ECP project for supporting this work, and the NERSC and OLCF for providing computational resources. We also thank Quincy Collier and Søren Beiner for their help regarding HDF5 and Danqing Wu for helping us understanding the E3SM I/O module. The log-based VOL is available at the link above. Okay, thank you.
Great. Thank you so much, Kaiyuan. Any questions for Kaiyuan about the log-based VOL? So one question I have is related to the time that is being spent in the I case. If you go back to that slide, what is the difference between G case or F case and I case? I mean, how much difference is there in terms of the number of I/O required?
Oh yeah, so if we see the previous slide, you can see for the I case you have 542 recorder variables and the 240 records.
Okay.
So if you multiply these two numbers, you got more than 130,000 H5 DRAM codes.
Mm-hmm.
So those numbers as those small overhead adds up with this number of H5 DRAM code. But if you see for all other cases or data sets, they either have a large number of variables or some large number of records, but none of them have both at once.
Okay. And how many files are you creating at the end? Is it still one file in the log structured format, or are you creating multiple small files?
For now, this is not using subfiling. So for each HDF5 file, we have one corresponding file. It's the same HDF5 file, except we instrument another groups and attributes and data set to store our log-based structure, but it's within the same HDF5 file.
Oh, you got muted, Kaiyuan.
Oh yeah, okay. Yeah, so it's only one file and it's the same HDF5 file.
Okay. And did you also give it a try for reading the log file and see how that is doing? Like, because now you have to go to the find the locations of each log structure piece of data and then go to the log and the actual data itself, right? So did you also give it a try for feeling of how the read performance is?
No, we didn't collect any read performance, and we don't expect it to perform well. You know, that's the inherent disadvantage of log-based storage layout.
Right.
Yeah, so the target application is for those where reader performance either doesn't matter or reading don't actually happen that often. Yeah.
Okay. Yeah, this is good for checkpoint files, type of things that you just dump the data and then.
Yeah, that's an obvious application where we write data just for backup. Yeah.
Okay. Right. Any other questions? Okay. If not, thank you, Kaiyuan, again. And it's a very nice work. And in ECP, this is going to be very useful.
And just a comment once again, appeal, please register your wall connector with us so we can advertise and people can start using it.
I think it is still a prototype stage, but it would be good to register it though.
Right, and okay, we'll talk offline, but yes, it's very useful wall connector.
And also, did you try with the latest API, Kaiyuan, or still using the 112 API?
We are using the latest developer branch, but to our understanding, 113 haven't been officially released yet. So if after that is released, we plan to move to 113 and stay there.
Okay. Yeah, if you're connecting with the developer branch, I think that is pretty
much. But developer branch at which time shot, right? At which time, right? So yeah, we'll be talking to the group and we'll help to move them to 113.